Welcome to the Chapter 55 wrap-up. So we left off when we were talking about this idea of primary productivity, how well you can capture energy from light to make organic molecules, or from chemicals in some cases. Chemosynthesis can work. And we talked about the idea of secondary productivity, of how well that energy gets moved up the trophic levels. So when we analyze this, there's going to be several ways of trying to look at this idea of energy flow, this transfer. And most of them are going to look like pyramids. All right, so you've got the pyramid of numbers, which is where we're going to look at the numbers of individuals that are autotrophs at the bottom, these primary producers. Then we can look at the herbivores and the carnivores as we go up in the levels. And you should see a general pattern where the numbers are highest at the bottom, and then they're going to diminish because there's less energy available to those first level consumers, and then diminish again because there's less available to secondary, etc., as you keep working your way up, until eventually you just don't have enough energy because it's flowing, it's diminishing as it goes. You won't have enough energy as you get to a specific height, usually at most 5 or 6 levels. Now, sometimes it will be a bit weird though if you're using numbers, because things like a forest where you might have very few but huge trees that put out a tremendous amount of leaves, so there's a lot of food that's there. If you were counting each leaf as like a blade of grass, you would have a huge number here. But because we're just looking at individual organisms, those trees will show up as relatively few. So don't be thrown off occasionally if you have kind of some oddballs. They won't always perfectly fit this exact pyramid structure. Sometimes they'll be a bit odd, especially if you're just looking at numbers. You can also look at biomass. So once again, this will be essentially dry weight. And so you typically will get this pyramid pattern once again, that you have the most biomass of your primary producers. Then you're going to have a smaller number of biomass once you get to your herbivores, because some of that energy is lost. They can't use it to make their own organic chemicals or to store their own organic chemicals. They have to burn some of it to do respiration. And then the process continues as you work your way up. Now, once again, there can be some oddballs, usually aquatic, because some phytoplankton reproduce very, very quickly, but they're not very long-lived. They tend to get eaten rapidly, and so there's actually not a ton of them at any one given time. So you can, in some cases, actually have more herbivores than you have the autotrophs. But that's almost always going to be an aquatic type thing that you'll see, and even then it's not the most common aquatic type thing. And lastly, we have good old-fashioned energy. And so with your energy pyramid, you should consistently see that you have the biggest amount of energy at the bottom, which makes sense once again. That's the primary productivity. And then it'll diminish each step you go up. This typically is the one that most reliably is going to give you a pretty good, pretty concise pyramid shape that we're looking for. Some of these other ones we've said can be manipulated a bit to where they're not always a perfect pyramid, but these guys are pretty darn good. These S guys that are sitting off to the side here, that refers to saprobes. And so these guys are actually the ones that are like the decomposers, the detritivores. These are the ones that are taking the energy from all of these groups and processing it to put the nutrients back in the soil. So they break stuff down. Now, moving away from energy, which of course was going through and flowing and kind of diminishing at each step, and by diminishing we mean just being given off to the surroundings, so it's no longer usable to the biotic stuff, to life. But at this point we have chemicals that we can look at, which commonly will be referred to as nutrients, because many of these chemicals are used to build organic chemicals that we need, to build organic compounds that will, like enzymes that help us function. So we're going to refer to the process of these guys moving throughout the environment, throughout the ecosystem, as biogeochemical cycles. The bio refers to the biotic component, so the living stuff that holds these molecules, at least for a while. And then the geochemical process will be the abiotic, where they can be also stored in rocks, they can be stored in water, they can be stored in soil. There's plenty of other places that they can oftentimes exist that are non-living, that are part of this transfer. That's part of how living things can get hold of them. And these things do not flow. They're going to cycle. So they're going to transfer from one thing to the next, but this should be 100% transfer. None of it's being officially lost. Worst case scenario, it goes into the abiotic pool of resources where it can later be accessed again. It's not like with energy, where oftentimes it's given off as heat, and that heat doesn't necessarily ever translate back into chemical energy again. Now, we'll start off, and we're just going to discuss a couple of these quickly to make sure you guys get a grasp of what I'm talking about. So we have the water cycle, and with the water cycle, you'll have evaporation and transpiration. Together, we oftentimes call that evapotranspiration. So don't freak out if you see that. It's just these combined. And so the transpiration and evaporation are what basically get the water up into the air. Now, when water's up in the air, you can have condensation, which allows the water to fall back down. And then from there, it can be absorbed into the ground, which become part of the groundwater. That's kind of longer term storage. It can obviously become part of the rivers, streams, lakes, oceans. That's also going to be a bit more longer term abiotic storage. And then it can be put into organisms because we're made up of mostly water. So you can have certainly the biotic component that we need to drink water. We use water. We're made up of mostly water. And so that's all going to be part of this as well. So the water cycle will be the shift from organisms that have water and use water. We're constantly getting rid of water. I mean, even just going to the bathroom. And then that's going to be going somewhere else. And that can be, once again, up in the air if you've got evaporation. It can be groundwater if you're talking more long-term storage, as well as just rivers, lakes, and streams. You also have the carbon cycle. So this one I like discussing because it's important for animals. This is also one of those that you guys will use in your aquariums. And you have a bunch of things that are naturally going to be producing CO2. So you've got plant respiration, you've got animals and decomposers that are doing respiration. So we're all producing CO2 that's then going up into the air typically, atmospheric CO2. And then that's going to be stored in several places. You've got where there's a fair amount of storage that occurs in waters, so especially like oceans, lakes, although there are organisms in those oceans and lakes that are also producing CO2. Animals, obviously the algae and such not as much because they're also using it, but decomposers. And so there's also going to be some CO2 being released. So overall, these kind of cancel out. So if you look at the water, it tends to kind of cancel out how much it's absorbing and releasing. You also have plants, algae, etc., that do live on land, primarily plants, of course, that are doing photosynthesis, so they're also storing CO2 in that way. And this tends to cancel out most of the respiration that you would get from plants and most of the respiration you get from animals and decomposers, with the exception of some of the intense stuff that humans have done with like raising livestock and such at higher concentrations than what we normally would. So there will be a little bit of excess based upon how we're using the land resources, because we tend to, with things like farming, we tend to be a bit more intense, so there is a bit extra CO2 that gets put out versus being taken in by this process of photosynthesis. And then obviously you've got some that get stored as things die. You can get formation of things like fossil fuels. You can get where there's this rich carbon material that gets stored longer term geologically. And that's what it's showing here with our amounts of coal, oil, natural gas that's being stored long term. And obviously humans burning this, anytime you burn a fossil fuel, you release a bunch of CO2. And this is also one of those things that tends to be excess. It's being put out there, but it's not really biotically capable of being stored rapidly enough. And so this is why what people talk about the high amount of fossil fuel use being one of the major things that indicates global warming, or at least the rising levels of CO2. And that's because normally the biotic stuff kind of cancels itself out as far as releasing and storing. But this abiotic release, like burning fossil fuels, is not being stored properly, so we can see clearly that our amount of CO2 in the air, atmospheric, is going up consistently over the course of decades. So that's the carbon cycle. The nitrogen cycle, which is the last one I'll do right here, this one's critical because for plants and algae, nitrogen is one of the most important, we'll say elements here, although it can be tied in with other things for molecules, that they need to grow. So when you look at fertilizers, the very first thing that it talks about usually on fertilizers is nitrogen. They have a rating called NPK, nitrogen, phosphorus, potassium. Those are the three most needed. But nitrogen's first. It's one of the most common guys. So you tend to have lots of nitrates, lots of these nitrogen-rich compounds that are in fertilizer because many plants desperately need that nitrogen. And so nitrogen itself is stored primarily in the atmosphere. This is the long-term abiotic storage. It's N2, it's pretty inert, it doesn't like to react, so it's like 80% of the atmosphere just sitting there pretty much saying, I'm not going to do anything. But there are some bacteria, and only bacteria, that can actually fix nitrogen. So they can take nitrogen, and you can see this over here, these guys, and so they can take nitrogen and they can convert it into other nitrogen compounds. Typically it's going to be more of like an ammonia type compound, which then other guys break down into other compounds such as nitrates is usually where they end up as. They go from ammonia or ammonium, depending on the pH, to nitrites to nitrates. And so this is the safest one. This is the one that plants like the most, is nitrate form. This is also in your aquariums. What you're doing is you have bacteria that take the ammonia or ammonium, depending on the pH. Remember, just ammonia is just NH3. It's just a slightly different version. And so it's going to take these guys and convert them to nitrites. And then there's other bacteria that convert nitrites to nitrates. Because this one is fairly toxic, And when you're talking about ammonia, ammonium, these are very toxic. So this one's, very unhappy for life. This one, I guess, is a little bit more in between. It can kill you if it's in fairly high amounts, but nitrates are by far the safest. Those have to be in very high amounts to actually kill you. And plants, algae, they love this stuff. So it doesn't stick around as long, whereas these other guys are not as easy to use when you talk about ammonium, if you talk about nitrites. And so eventually the nitrates especially get used by plants, algae, a lot of these primary producers, and they'll use it to build the various organic compounds they need. And then those organic compounds then get eaten by heterotrophs, as well as decomposers will break them back down, which can put them back in the soil or back in the water if we're talking about like an aquarium. So this can just be a big deal because a lot of animals too will produce ammonia as a byproduct of breaking down things like proteins. And so they will then urinate or in some way excrete waste. And a lot of times that will contain some type of ammonia compound or some type of modified ammonia compound. Like humans, it happens to be urea. If you're a bird, it'd be uric acid. But for like fish, it's pure ammonia or ammonium, once again, based on pH. And that's going to then go into the water. And if you have too much of it, that's what kills your fish. So if you just get a brand new fish, put him in the water, and then suddenly he's gasping for air a day later and dies, that's because he was excreting ammonia. That ammonia then attacks his gills and burns them, so he can't breathe properly and he dies. Now, if you have the right bacteria there, this is why you cycle a tank. This is why you put sponges in there for the bacteria to grow on. The bacteria, then specifically we're talking about these guys towards the bottom here, these nitrifying as they're called bacteria, they're going to break down that ammonia or ammonium into nitrates and then, well, eventually nitrates through nitrites, which then won't be as harmful. So then your goldfish will be fine. So this is why they always tell you, be careful, don't just load up your tank with a bunch of fish unless you know those bacteria are there, unless you've cycled it, which means that you have done the nitrogen cycle. You typically put just a little bit of ammonia in the tank, just a small amount, and then you let it sit for about a week with whatever that sponge is in there or your filter running, which allow these bacteria then to develop, so the bacteria will be there to save your fish. Now the last bits we have are just human impact. So with human impact, we've got biological magnification as one of these kind of cool things that happens. And this is where, I guess, cool, sad things. We have pollutants that are in water. And the small guys in the water eat very small amounts or small amounts diffuse into them. But one way or another, they get very small amounts. So in this case, we're looking at mercury. Now from there, though, the guy that eats those small guys has to eat a lot of those small guys. So it gets their small doses, but it gets many of their small doses. So its amount of toxin now goes up a fair amount. In many cases, it can be like a factor of 10. And then the bigger fish that eats the small fish has to eat a lot of them. Right? This is just how it works because it doesn't get all their energy. So it has to eat more, so its number gets even higher as far as the amount of pollutants it has. And then as you keep working your way up the food web, food chain, you keep getting a larger and larger amount of pollutants in each of these bigger and bigger organisms. And so we call this biological magnification. And so this was what makes even relatively small amounts of pollutants an issue, because if we're then eating some of these bigger organisms, that have been at the end of this process, fish is a really common example. So a lot of these bigger fish that we like, we then can get larger amounts of these pollutants with them, like mercury, which can cause serious problems if you have too much, especially if you're pregnant or may become pregnant. And so that's why you'll see that they'll tell you, based on the type of fish that you're eating, you have to be careful how often you eat it. You can eat lots of these little guys, but the bigger guys you got to be very careful about. Now, another thing we'll discuss that's kind of a human effect is greenhouse effect. We've talked about how humans are burning up a lot of these abiotic carbon stores and releasing extra CO2 in the air. And so we can see that over the course of, say 1850, 1840 here through today, you can see that there's been a fairly sharp spike in the amount of CO2 that there is present. I mean, it's blatantly obvious here. We've gone from, if you're going by parts per million, we've gone from around, say, 290 all the way up to where now we're closing in at about 400. So this is a large change that we've had in the past, 150, 160 years. You can also see the temperature has, in general, trended up and increased over the same amount of time. Now, this is why a lot of people talk about the anthropogenic, if I've said that right, greenhouse effect, which is human caused. because we're the ones burning the fossil fuels, we're the ones that are intensely farming, producing extra CO2, and it's that extra CO2 that has allowed the amount of CO2 in the atmosphere to go up. Before this, when it was just biotic stuff that was generally releasing and storing it, it was fairly balanced. It was pretty consistent. But we kind of imbalanced it with the amount that we have produced extra from our personal uses. And that has mapped pretty well with temperature. If you look at other stuff that people like to sometimes indicate, like sunspots, saying that there's other causes of this, you can see it's pretty clear sunspots do not cause this. They don't mirror this at all. You've had low sunspot activity during some of the sharpest rises in temperature, so CO2 much more closely mirrors it. So this is some of the evidence that we look at, that we see, that demonstrates that this greenhouse effect appears to be very valid, and it appears to be tied to our CO2 production. Some other things that we've done as we wrap things up is we have produced a bunch of guys called chlorofluorocarbons, or CFCs. This is commonly produced by things like Freon that are refrigerants, so you can have air conditioning, so your refrigerator works. But when these guys get in the upper atmosphere, they react with and damage the ozone. They basically get rid of the ozone. And so when you look at the concentration of ozone, you can see over the Antarctic, over the poles, that it's very, very thin. Purple's the thinnest. Red would be the thickest. And so when they talk about like the hole in the ozone layer, they're referring to these areas now where it's incredibly thin, the amount of ozone that's there. And that matters to us because ozone will form and break apart naturally as it absorbs UV light. And so UV radiation is a mutagen. It can lead to mutations, cancer, a bunch of bad things. And so we want this ozone layer to be there to prevent that UV light from reaching us. And so as it thins, that means more UV light comes in. That means you have to have more fears about things like skin cancer. And then we've done a lot of habitat destruction. Now, some of this is to build cities. Some of this is because we want to do things like farm. Some of it is we want lumber, or we want resources that are there. We want to mine. We want to get something extracted from the ground, so we damage it. And so we've done a huge amount of habitat destruction. We've affected what habitat is in which area tremendously. And a lot of this comes back to kind of what's driving this and how can we fix it. And so one part that a lot of people would say is overpopulation, too many people, and so our resource demands are so high that we have to keep going and damaging more and more stuff to try to make it do what we want and not just be nature. And then a lot of that also ties, though, into resource use, because different people use different amounts of resources. And so when you look at this chart here, the paler it is, essentially the less resources that you're using. The darker it is, like us, the more resources that you're using. So if all humans were using kind of a more African, some Latin American type amount of resources, we could have the amount of people we have now, and we probably would be fine because we'd all be using so few resources, we wouldn't be demanding that much of the environment. But as you get more and more people that are having higher resource usage, that are demanding kind of more stuff. So as you're looking at that resource usage per person, per capita, going up in many countries like China and India, which is, great in a sense that they're getting to a point where they can have some of the luxuries and the accommodations that we have and enjoy. But the negative is we need more resources then to provide them with those. And so as resource use per person goes up, this also places a huge demand on things. So while maybe you could have 10 billion people if we all lived like we were from Kenya, you can't have 10 billion people that live American lifestyles. You might be able to have 1, maybe 2 billion that live that type of lifestyle, and that would equate to 10 billion people living a lifestyle of a Kenyan or an Indian or something else where they use a lot less resources. And so that's why there has to be two pieces of this puzzle. It's not just about how many of us there are, it's also about how demanding we are.